Hi everyone, I'm going to talk you through the atomic spectrum of hydrogen lab. As normal, I'll give you a bit of a checklist. Alright, so this I've printed, but you actually don't have to print it because it's actually at the group site, GRP 101 on Canvas, as a fileable document, meaning you can keep it on your computer, do the math on the side and just fill in the blanks. Okay, so there's no need to print this. I'd say, just edit on your device and then you can just, email it back as normal. Okay, so checklist. 1, download fileable document, right? So look online at the GRP 101, 101. Download that document. I've actually printed it, you don't have to, you can just fill it in, okay? All right, so it's all electronic, kind of nice. And 2, obviously, watch the 2 atomic theory videos, right? Okay, so this makes a lot more sense. In fact, you can't really do this unless you watch those videos. So watch modern atomic theory and modern atomic theory applications, okay? Watch those 2, and then I'll kind of give you the background you need to answer these questions. And so you'll download this, you'll watch the videos, answer the questions, and then submit via email. Now remember, not Canvas, right? Canvas email is still a bit buggy, right? So just from your regular email account, just attach the completed document, put your name in the file name. And that's going to be due on Wednesday, okay? So I'll put this up today, which is Monday, give you Tuesday to do it. And get it, Tuesday and Wednesday, right? Get it back to me before the end of the day on Wednesday. All right, so hopefully that makes sense. Now, what I'm going to do, I'm actually going to run through my Prelab I do actually in class, okay? So it kind of makes for a nice kind of common sense kind of introduction to this, all right? So obviously we're going to look at the atomic spectrum of hydrogen. Now, turns out that we choose hydrogen and only hydrogen because guess what? It's just got that one electron. So that electrodynamic stuff we talked about, how it really kind of messes up things, okay? Unless you're Feynman and you get that Nobel Prize, okay? So hydrogen is actually the simplest atom. There are no electron-electron interactions because it's just one electron. So the math actually simplifies, okay? So we can model the spectrum of hydrogen with simple mathematics. It's empirical math, but it works perfectly, okay? Because hydrogen is a very simple system, all right? And the objective is to understand the relationship between emission spectrum. Now, we'll talk about this in detail in a second, all right? But think of a neon light, okay? Think of a Budweiser sign, okay? Neon lights are false advertising, right? Because only neon is, for example, I think it's kind of a purple color. And different gases actually give out different colored lights, okay? So you see blue lights, red lights, purple lights, okay? So different colored gases, different elements when excited in the way we'll talk about have an emission spectrum, a certain color of light that comes out, and each gas emits a different color light. Okay, so there's more than just neon signs. There's argon signs, there's nitrogen signs, there's helium signs, there's different gases give different colors, okay? So we're going to understand the relationship between the color of light that comes out of an excited gas, essentially a neon sign, right, with whatever gas you want inside, and the electronic structure, the internal geography of an atom in terms of where electrons are, because it's where those electrons are and where they move to that eventually generates this light, right? And electronic structure. So think of the geography of the atom, the parking lot. We're going to, relate that to the light that comes out of an atom when excited, all right? Now, to kind of explain this in a kind of a common sense way, how do neon signs and, if I'm kind of more generic, fluorescent, make sure I spell this right, fluor, So a light tube, we call it, right? So it's basically very simple, all right? So, you know, those old style lights you have in the kitchen, you turn them on and there's a fluorescent light. You know, you see the Budweiser sign, that's the same kind of concept, okay? So how it works is you have a glass tube, right? Okay, and you cap off the ends and you kind of have these electrodes, right? And inside you have a low pressure gas, all right? So you have a low pressure gas inside the glass tube. Fair enough. Now low pressure, right? Because we talked about it a little bit when we talked about, remember the ion cannon? Yeah? Ions or electrons can only fly across a gap if there's nothing in the way, all right? So because it's low pressure, when we attach this to the electricity, we have a large voltage, it's a large potential difference. It's like a ball rolling down a hill, right? So if we have a plus and a minus end, electrons will basically shoot across here. It's literally, when we turn on the electricity, lightning in a ball. Okay, so we have electrons jumping across this gap with gas particles in the way, right? Okay, so high voltage, low pressure gas, and you can have any gas you like, right? Neon is the classic, but you can have any gas you like, different gases again to give different colors, okay? Now, interesting, what's going to happen, and there's one, right? So if I look here, eventually a gas particle will be in the way of an electron and it will have a big impact, right? Now, the atom itself can do one of two things. It can either absorb that energy somehow and survive, or be just obliterated. It can be smashed into pieces. Okay? It actually survives. And the question is, well, how does the particle absorb the energy of collision? Okay, well, if we go down here, all right, so here's my atom with its energy levels, right? Okay, so maybe I've got an electron in the first level. I'm going to zoom in, right? So just like we talked about in the packet, I'm going to do an energy level diagram. Okay, so I'm going to zoom in. Okay, I'll keep the curves just for effect, right? So here's the nucleus. N equals 1, N equals 2, N equals 3, right? And that's a positive nucleus, right? Okay, so if you think about it, so the electron's just there, minding its own business in its regular place, right? N equals 1 or whatever, maybe it's a 1s electron or something, right? And then the atom gets hit by this projectile, right? It's like, you know, you go to the county fair and you see the little cans in the triangle in the pyramid and you try and knock them down with the ball. It's like it got hit, right? Okay, so what's going to happen? This has to absorb the energy or be destroyed, right? So what it does, it actually promotes an electron to a higher level. Now think about that, right? So it goes from here to here, yeah? I'm pulling against the positive nucleus, right? So pulling an electron away from a positive nucleus costs energy, the energy of the collision. So internally, the energy is converted, right? So instead of ripping it apart, it's converted to promotion. And that's what happens. So we promote an electron, right? So if you write that on the side, electrical energy, you know, this spark that's going through here, right? Those electron atom collisions. Electrical energy excites, let's use old school. It's not really true, is it? But in our model, it makes sense. An orbiting electron, right, in the lower level is excited, and therefore it goes from a low to a high orbit. Okay, it's like, you know, gravity in objects, right? So it takes energy to throw the pen in the air, right? So I give the pen some energy, it goes higher, yeah? Okay, all right. So there's some energy involved in that jump, right? So from here to here, there's some energy involved, right? So delta E, the incoming electron's energy, is equal to this gap. The more hard to hit, the bigger the gap it will jump, right? So it jumps the same gap as the energy it has. Interesting. So if you really want to promote electrons, hit it with lots of energy. If you want to just go up a little bit of energy. So E jump equals, now these are energy levels, right? Remember, if you watch that packet, watch that video, we talk about energy levels, right? So we don't measure the distance in atoms, we measure how much energy it costs to go a distance, right? So to go from the nucleus to layer 1, it costs E1. To go from the nucleus to layer 2, it costs E2. From the nucleus to layer 3, it costs E3. That's the energy level, right? Okay, but if I want that gap, it's essentially, and unfortunately I don't have a different colored pen, right? It's this distance minus this distance, right? So this plus this is the whole thing. So if I just want this, it's the whole thing minus the first distance, right? So it's E outer, which is this one, minus E inner. Okay, so if I want the gap, it's how far the outer is minus how far the inner is. That's what I'm trying to say. Okay, fair enough. We can't measure that, okay? We can't measure the distance on the way up, unfortunately, but good news is we can measure the distance on the way down. All right, so if I fold this over, okay, now what's that classic expression? Classic expression is what goes up must come down, right? So let's just kind of think about what we got. Layer 1, layer 2, layer 3, right? Currently we've got an electron sitting up there in layer 2. It's not where it should be. If you like, it left a gap down here, right? So what goes up must come down. When the energy dissipates through molecular collisions or other means, basically turns to heat, this electron will jump back down, okay, or fall back down, all right? So the excited electron, all right, is unstable and will drop to a lower level. Now, I'm actually writing on the back of the packet here. This is all explained in the front of the packet, which I'm just paraphrasing in a more kind of common sense way. So you can read through the packet for clarity or a different explanation, but it's really the same thing. All right. So now we have that delta E again, right? So delta E is the same as before. Delta E of the drop, it's the same gap as before, right? It's the same gap as before, but we're coming down, not going up, but it's the same distance or the same energy difference, right? Okay, equals E outer minus E inner. Now here's the thing. It took energy to push it away from the nucleus, right? So the energy of the impact pushed the electron away from the nucleus, yeah? When it comes back, I get the energy back again, right? Interesting. So what does the atom do? It's basically generating energy when it drops back down. Well, it just throws it out, right? What comes out is a packet of energy, a quanta of energy called a photon, right? A photon is nature's energy carrier, yeah? So light from the sun is carrying energy from the sun. We get warm from the sun, right? That's just a form of light, yeah? So photons carry energy from place A to place B. So the atom emits a photon, a particle of light, which carries the energy away. That's called a quanta, right? Now, you can read it in the packet, but, so this is the geography term. That's the inner kind of gap in the atom, you know, how far an energy is between the energy levels. That's the internal geography of the atom. That relates to electronic structure. 2, the photon energy. The energy of the photon is Planck's constant times its frequency, right, which is c, its speed over its wavelength, right? So c over lambda is frequency. That's the speed of light over the wavelength. And the wavelength, if you remember the iron experiment, is the color, right? So that's the color. So a certain wavelength of light will come out, right? And that wavelength will depend entirely on the gap, yeah? So it's reciprocal, so a shorter wavelength is a higher energy, it's a bigger gap, right? A longer wavelength, if you're dividing by a big number, is a small number, right? Okay, so a long wavelength is a small gap, a short wavelength is a big gap. Interesting. Okay, all right, so that's an important relationship. You'll see this on, you know, future chemistry tests and things like that. And physicists, if you take a physics test, it's the same equation. They just do it on energy per photon, right? So it's usually in something like electron volts or something. The units are neither here nor there. In chemistry, we like per mole, right? So we do kilojoules per mole on our energy level diagrams, as you've seen. Physicists tend to use energies in electron volts, the energy of a single electron. Okay, so that's an important relationship, right? It's a key relationship, all right? There's a relationship between color and geography. The gap distance in terms of energy is related to the color of the light that comes out. So whenever an electron drops from one layer to another, light comes out. The bigger the gap, the shorter the wavelength. And if you remember the spectrum, and I'll give you kind of a heads up for your experiment here, okay, if I have, there's the visible, all right, off the visible end is the ultraviolet, off the red end is the infrared. That's short wavelength, right? That's long wavelength, okay? So in terms of our energy level diagram, if it's a short wavelength Ah, interesting. That means it's higher energy. It's dropping from a high level to a low level. In hydrogen, that's dropping down from somewhere to level 1. It's dropping all the way to the bottom. Yeah. If it's slightly more energetic, it's dropping to layer 2. And if it's super low energy, it's dropping to layer 3. Okay. So if I drop all the way to the bottom from a higher level, I think that's called the Lyman series, right? That's ultraviolet, can't see it. If I'm dropping from a higher level down to layer 2, it's in the visible range. We would actually see that, okay? So I've got numbers for you for the visible range. That's called the Balmer series. They talk a lot about that in the book. Balmer is famous because it's the one you can see. So there's your big hint for the math, right, later on. If it's visible light, it's dropping from somewhere to layer 2. That'll allow you to do the assignments a lot easier. Okay. All right. So that's the basics. Now let's maybe take a look at your experiment, okay? So all right. So you can just read through this. Now these are assignments, right? So these are wavelengths of light that come out of the hydrogen, right? So these are all transitions, and later on you'll actually do the math and you'll work out some wavelengths for certain transitions. Hopefully they're going to match, right? They're going to match. So these are actual numbers that come out of the experiment. Your job after you've done the match, well, is it level 6 to layer 2 or something, right? So you're going to make an assignment, an end-to-end assignment, right? So, and it always goes from a high number to a low number, but that will be completed later, okay? So we'll do the calculations, talk about that in a moment, okay? Then we'll look at compare them to the hydrogen, and you can make these assignments. Okay, now, and it talks about the Balmer series. So let's look at your actual experiment. Now, what we're going to do first is make the map, right? Okay, so if you look in the back, have this one on the side, right? Have this on the side. We're actually going to make an energy level diagram. Okay, so there's the energy level diagram. It starts at 0, right, and it goes down deep. Remember, we count backwards if you watch that video, so it's kind of like a well, right? Okay, so what we're going to do, we're going to find out where the energy levels are, right? So energy level number 1, so n equals 1, how far down is it, right? So let's just do that calculation, right? Now to do this, you need an equation, right? And let me just find it. It's in the packet, but I'm going to kind of find mine. Okay, here it is. Here it is. E n equals, and we like kilojoules, right? Minus 1312 kilojoules over n squared, right? So let me find my ruler. Okay, so the depth of the energy level, how far down it is on this chart, equals a constant minus 1312.02 kilojoules over n squared. Now, if n equals 1, well, I'm just dividing by 1, right? So it's just 1312.04. So I get my ruler. There's 1312 about there, right? Okay, and I draw a line. That's n equals 1. Fair enough. That's my first energy level, right? Ah, easy, right? If n equals 2, it's minus 1312.04 kilojoules over n squared is 2 squared is 4, right? Quick calculator. 1312.04 divided by 4 equals 328.01, right? 328.01. Now, 328.01 is about here. N equals 2. It's a big gap right now. What's going to happen, if you remember the discussion from the packet, these asymptotally approach 0, so they get tighter and tighter and tighter and tighter. That's why one atom isn't as big as the universe, right? Okay, so you'll find that the energy levels crunch together, okay, and do up to n equals 6, right? So this is going to be half the distance, and you get 6 lines across there labeled, okay? 6 lines across there labeled. Fair enough. Okay. Now, so let's go back to the old packet here. All right. So we did that math, okay? Number 1 was minus 13, what do we say? 08, right? And then minus, what was it? Oh, let's go my calculator. 328. Okay, so it wants you to work out the first 10, and you'll need to do that for maybe this later, okay? But when we talk about transitions, we're going to do 6, right? Actually, it says 5 down here. So 5, I'm going to change my number, okay? Do the first 5 on your graph, okay? So here, do up to n equals 5 on your graph, okay? Okay, energy level diagram, okay? So let's just recap. That got confusing, okay? Find out how far down each of these levels are, right? Oh, that should be over here. That's just number 1 and 2 and 3, etc. Okay. Do it for the first 10. Okay, so you're going to be dividing for that last one over 10 squared and 100, right? Okay. All right. And then take the first 5 and you're going to fill out, oh, actually it is 6. You're going to take the first 6 and then work out the difference, right? So let's just do one, right? So here, this was minus 328, and that was minus 1312, right? So if I want, oh, turn it up. If I want that distance, it's 1312, just do, I want the difference, right? So just do the whole numbers, right? So 1312 minus 328 equals 984 kilojoules, right? So the difference between the layers 1 and 2, okay, so let's just recap. I used the equation to find out how far down in the well these layers were, all right? Then if I do a transition between 1 and 2, I just subtract the two numbers. That's delta E, right? Okay, fair enough. All right. Now, that's great, but it doesn't tell us what we need to know, which is the wavelength, okay? So we use a separate equation for that. The separate equation is lambda in nanometers equals 1.9627 times 10 to the 5 over delta E, all right? So if I just stick in 948 as delta E, I get the wavelength for that. So lambda equals, and I can work it out, okay? Now that's what I want you to do, okay? So I want you to kind of do nests, right? So these will get closer together. I'm not sure what the numbers are, but then do another one, right? Okay? Find out these two values, yeah? Okay, and that's what I want you to do. Draw this kind of nested energy level diagram, okay? Now, in terms of the numbers you calculate, they appear in table 3, okay? So in table 3, if we look here, okay, I just went from 1 to 2, right? That was 984 kilojoules, yeah? And then whatever the wavelength is for that, yeah? Okay, so it's like, hey, 1 and 2, it's this, right? Okay, and this gives you all the possible combinations, okay, between 6 all the way down, okay? So 6 to 1, 6 to 2, 6 to 3, 6 to 4, 6 to 5, and then 3 to 2 or something, right? So this is a grid kind of, right? So you fill out this whole grid and write the answers here, okay? All right, okay. Now, this is basically the bulk of it, right? Now, if you remember, I said transitions to layer 2 were visible. Those are ones you can see. So when you look at the hydrogen spectrum, here's your big clue, right? Transitions to layer 2 will be here, right? So we're ending up at layer 2. So these numbers, particularly the wavelengths, will hopefully match what you see for the true numbers in hydrogen, right? So you'll have an observed wavelength and a calculated wavelength, okay? So look down here for your calculated wavelengths. they should match an observed wavelength, right? And because when you did your math, you worked out this one and you assigned a transition. So it's going to be from somewhere to layer 2. That's going to be in there, right? So the first one, and you can do them in order, right? Okay, so maybe it's the shortest distance, which is layer 3 to layer 2, right? N equals 3 to N equals 2. That's actually going to have the longest wavelength, right? Okay, and then it's going to be 3 to 2, 4 to 2, 5 to 2, 6 to 2. 6 to 2 is the biggest gap. It's going to have the shortest wavelength, probably in the 410 region, somewhere around there. Okay, all right. So calculated wavelength from your table. Probable transition, again, from your table. So wherever you got the number from, it tells you the transition. 3 to 2 would be this, 4 to 2, 5 to 2, 6 to 2. Energy, well, that's in the table as well, and then observed wavelength should be close, right? Should be close. All right. Okay. The rest of it is basically questions. Okay. So, if you remember my pre-lab there, kind of talked about that already. So on the high energy side is ultraviolet, on the low energy side is infrared. So if you're out of the visible range, either on the high or low side of for wavelength, you can kind of answer these questions, right? All right. First ionization, that's an interesting one, right? Okay, first ionization. Now what is the definition of ionization? Well, I'm taking an electron all the way from the bottom of the well and pulling it to the surface, right? So it's kind of a no-brainer if you think about it. How much energy does it cost? How far down is the well? If you know the depth of the well, it costs that energy to bring it back up to the surface, right? You know the depth of the well because it's the energy at the first energy level. So the first ionization energy is easy. It's how much energy it costs to pull one out from the bottom. I'm not going to tell you the number because you already worked it out. Okay, so work that one out. And then the other questions, hopefully pretty straightforward. It's just a conversion. So you convert kilojoules per mole, which is chemistry numbers, into physics numbers, joules per atom, electron volts per atom. Okay, and you know, they have the conversions in there. All right, so all in all, it's a lot of busy work, got to be honest, right? Lots of computer, calculator stuff, lots of calculator stuff, but as long as you're systematic, okay, complete the first 10 energy level positions, all right, write the first 6 on your energy level diagram, okay? Then, once you've got those levels figured out, you can figure out the difference in energy between levels, right? Write it in, okay? And this is like a train timetable, for those who remember those, right? So 2 to 1, we did it, right? Use the equation to work out the wavelength. I showed you that equation. It's in the packet. And then to complete this whole grid, right? And then, I gave you the big hint, the Balmer series ends up at layer 2. So the numbers you get for wavelength should match those you see, quote unquote see for hydrogen, because any visible transitions end up at layer 2, Balmer series. Okay, and that'll allow you to answer the questions. And then just remember, hey, low wavelength is bigger gap, right? So if it's in the ultraviolet, it's a bigger gap. If it's in the infrared, it's a lower gap. Okay. All right, stop there. Get this to me by end of Wednesday. Okay, see you on the next one.